On a winter night in 1912 at the Lowell Observatory in Flagstaff, Arizona, astronomer Vesto Slipher began a meticulous observation that would change everything. He aimed his telescope at the faint spiral nebula Andromeda and recorded its light spectrum. What he saw was a startling shift in light frequencies, a clear signal that Andromeda wasn't just moving, but racing towards us at an unprecedented speed. It was the first true hint that our static, familiar universe was anything but. Vesto Slipher's initial measurements, published between 1912 and 1917, weren't just about Andromeda. He observed similar shifts in other spiral nebulae. He meticulously documented their spectral lines, noticing a consistent redshift in most, indicating they were receding from Earth at immense velocities. This pioneering work provided the first empirical evidence that the universe was not static but dynamic, with galaxies hurtling through space. Slipher's groundbreaking observations, though not immediately interpreted as cosmic expansion, laid the foundational bricks for future colossal discoveries. His findings presented a monumental challenge to the prevailing static model of the cosmos at the time. Just over a decade later, in 1929, Edwin Hubble used the powerful 100-inch Hooker telescope to precisely measure the distances to these spiral nebulae. By identifying individual Cepheid variable stars within them, Hubble proved that Andromeda and countless others were not merely gas clouds within our Milky Way, but entirely separate galaxies. This revelation instantly expanded the known universe, transforming our isolated galactic island into one among billions. Hubble then correlated these distances with Slipher's velocity measurements, establishing the groundbreaking concept of an expanding universe. His work definitively shifted our understanding of cosmic scale from a local to a truly universal perspective. Our home planet Earth, with its diameter of roughly 12,742 kilometers, feels incredibly vast, yet it is a mere speck. To put this in perspective, our sun is so immense that you could comfortably fit over 1.3 million Earths inside its fiery volume. Despite being a common main-sequence star, the sun alone dwarfs everything we experience directly, reminding us of our planet's relative insignificance in the cosmic ballet. This comparison provides a crucial first step in comprehending the true magnitude of space. Currently, Voyager 1 holds the record as humanity's farthest ambassador, traveling over 24 billion kilometers from Earth and into interstellar space. Launched in 1977, this tiny probe has been journeying for over 46 years, sending back data from beyond the heliosphere, the protective bubble created by our sun. Even at its incredible speed of 17 kilometers per second, it will take tens of thousands of years to reach our nearest star. Voyager 1 shows us just how incredibly vast even our local stellar neighborhood is. Beyond Voyager 1 lies the Oort cloud, a vast spherical shell of icy objects thought to extend up to a light-year from the sun. This distant realm, a relic from the early solar system, marks the true gravitational boundary of our solar system, far beyond the orbits of the planets. It's estimated to contain trillions of icy bodies, some potentially larger than Pluto, slowly orbiting our sun. Traversing this immense region would take millennia, highlighting the deep isolation of our star. The nearest star to our sun, Proxima Centauri, still lies an astonishing 4.2 light-years away. To grasp this distance, consider that a light-year is the distance light travels in 1 year, approximately 9.46 trillion kilometers. Even if we could travel at the speed of light, it would take over 4 years to reach this cosmic neighbor. This immense gap between stars truly emphasizes the vast, empty stretches that define our galaxy. Zooming out, our Milky Way galaxy is a majestic barred spiral stretching an estimated 100,000 light-years across. If you could somehow travel from one end to the other at light speed, it would still take you 100 millennia. Our solar system is just one tiny speck, located about 2/3 of the way out from the galactic center, in one of its spiral arms. The sheer scale of our own galaxy is almost impossible to fully comprehend. At the very heart of the Milky Way lurks Sagittarius A, a supermassive black hole possessing an incredible 4.3 million times the mass of our sun. This gravitational behemoth, though relatively dormant now, influences the orbits of stars and gas clouds for thousands of light-years around. Its immense pull dictates the dynamics of our entire galaxy, holding hundreds of billions of stars in its colossal grip. Observing its effects helps scientists understand the mechanics of galactic evolution. Within the colossal span of the Milky Way, astronomers estimate there are between 200 and 400 billion stars. Each of these stars, like our sun, could potentially host its own planetary system, some even nurturing worlds similar to Earth. Imagine the sheer number of possible planets, moons, and exotic celestial bodies orbiting in this galactic metropolis. This incredible stellar population makes our galaxy a truly bustling cosmic city. Our Milky Way is not alone. It's part of a humble cosmic neighborhood called the Local Group, a gravitationally bound collection of over 50 galaxies. This cluster spans roughly 10 million light-years across, dominated by our Milky Way and its colossal neighbor, the Andromeda Galaxy. These two giants comprise most of the group's mass, slowly pulling the smaller dwarf galaxies into their gravitational embrace. Our galactic home is intricately connected to this larger cosmic web. The Andromeda Galaxy, our closest large galactic neighbor, is a stunning spiral similar in shape to the Milky Way, but even larger, containing an estimated 1 trillion stars. It currently hurtles towards us at approximately 110 kilometers per second, setting the stage for a spectacular cosmic collision in about 4.5 billion years. This inevitable encounter will reshape both galaxies into a new, massive elliptical galaxy known as Mulcometa. Beyond the local group lies the Virgo supercluster, a sprawling collection of over 1,300 galaxies spanning an immense 110 million light-years. Our entire local group is just a small component on the outskirts of this much larger structure, gravitationally drawn towards its dense center. The sheer concentration of galaxies within the Virgo supercluster reveals how matter aggregates into immense cosmic cities. Observing its dynamics helps us trace the flow of galaxies across vast distances. Even the Virgo supercluster is just a minor component of an even grander structure, the Laniakea supercluster, meaning immeasurable heaven in Hawaiian. This colossal cosmic web encompasses over 100,000 galaxies and stretches an astounding 520 million light-years across. All galaxies within Laniakea, including our own, are slowly flowing towards a massive gravitational anomaly known as the Great Attractor. This vast structure truly defines our cosmic home on the largest scales. All these structures, from Earth to superclusters, exist within what we call the observable universe, the finite bubble of space from which light has had enough time to reach us since the Big Bang. Because the speed of light is finite, we can only see as far as light has traveled in 13.8 billion years. Everything beyond this cosmic horizon remains forever hidden from our direct view. This boundary is not a physical edge, but a limit to our perception. The diameter of this observable universe is not 13.8 billion light-years, as one might assume, but a staggering 93 billion light-years. This mind-bending discrepancy arises because space itself has been expanding since the light began its journey towards us. As light traveled for billions of years, the fabric of the universe stretched, pushing distant galaxies even further away. This rapid expansion ensures that what we observe today is significantly larger than its initial dimensions.